So up through now, all week, we've been talking about reactions that have one alkene. We've not talked a ton about alkynes, but really the majority of the stuff we've said about alkenes applies to alkynes. We just don't spend a lot of time talking explicitly about alkynes. Okay, I digress. We've been talking mostly about things that have one alkene. What if you have more than one alkene? That's a diene. Or a lot more than one alkene, polyenes, many enes, polyenes. Those dienes or polyenes could be conjugated, they could be isolated, or they could be cumulated. What does it mean to be conjugated, isolated, cumulated? Well, here are some examples. This top example has a double bond, and then a single bond, and then a double bond. It's conjugated. Double, single, double, conjugated. Double, single, 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 double. Anytime it's not double, single, double, we're going to call that thing isolated. And this one, this one that has two double bonds, one carbon involved in two double bonds, that's called cumulated. Cumulated, according to the previous slide and all the words on the previous slide, it's the least stable of the diene types. Conjugated is the most stable, isolated is in the middle, cumulated is the least. Conjugated is extra stable because of resonance. Isolated doesn't have any resonance. It's just like a normal alkene, really, and it behaves and reacts like a normal alkene with some exceptions. And cumulated, we really won't see many of these things, period. So when presented with a reaction like this, where you're told to draw the mechanism or predict the product, you first need to determine what kind of diene you have. After recognizing you have a diene, you need to determine what kind of diene you have. This diene is an isolated diene. And an isolated diene reacts very much like a standard alkene. If I were to react this alkene with HCl, we're going to make a carbocation, right? Yeah. This alkene with carbocation, this alkene with HCl would make a secondary carbocation. That alkene with HCl would make a tertiary carbocation. Which one makes a more stable carbocation? This one. So we're going to react this one. Why does it work like that? Well, we could draw ourselves a little reaction coordinate diagram. If I put a secondary carbocation on that little line, a tertiary carbocation goes below it. Oh man, that's real hard to see. Tertiary carbocation has a hump that's lower than the secondary because the energy of a tertiary is lower. So the tertiary will form faster. So in an isolated diene, you react the more substituted diene because that's going to lead to the better carbocation. So if I were drawing a mechanism, you know this mechanism like the back of your hand by now, right? Right. This carbocation is formed, and chloride attacks that carbocation. Ding-da-ding, ta-da-da. Yep. This is my one and only product when I add one equivalent of HCl. If I added two equivalents of HCl, well, I would react both alkenes eventually. But the alkene that makes a more stable carbocation is what reacts fastest and what you would choose to react with if you only have one equivalent of reagent. All right, let's do another one. So what kind of diene is this? This is an isolated diene also. This isolated diene, the two alkenes react independently. So I should have specified and just realized that I didn't. I've got one equivalent of HBr, one equivalent of acid. This one's a little bit harder to control maybe, but you cannot have one equivalent of water most likely because that's your solvent. You're going to have a ton of it. One equivalent of acid down here to try and control and make sure only one of your alkene reacts. Okay, so if I go north to this top reaction, even if the reactions do not make a carbocation, an isolated diene, the alkene that reacts is the one that would make the most stable carbocation. So in this diene, that's left alkene or right alkene, that's right alkene. So going north, that right alkene is going to react with HBr. Br ends up in the armpit, like that. Next, we've got acid and water added to an alkene, a diene, gonna react with the right diene again. OH ends up in the armpit, like that. And this bottom one, we've not seen an example like this so far. We're going to end up with the same carbocation that we ended up with in the others. I'm having computer troubles over here. It's not showing up. Come on. You can do it. We're going to end up with the same carbocation as the others. And this O is going to attack. Yeah. And then we're going to lose an H like water. And we end up with that. We made an ester. This ester is in the armpit, just like all the others. It's an isolated diene. Isolated dienes, the two alkenes react independently. Okay? What kind of diene is this? Oh, cool news. It's an isolated diene. So I react the one alkene that makes the most stable carbocation. Left alkene would make what kind of carbocation? Tertiary. Right alkene would make what kind of carbocation? Tertiary. Womp womp. What now? When both of them make the same stability alkene, so we have a tertiary carbocation sitting on the shelf, that stability of the carbocations does not decide my fate. The stability of the alkene decides my fate. The alkene, I'm going to try to put it on the same hump. The alkene that's lower energy requires more energy input in order to climb that hill. This lower energy alkene requires more energy input to climb that hill and make a carbocation. The alkene that's higher energy requires less energy input in order to climb that hill and become a tertiary carbocation. So, when the carbocation stability is the same, decision number one is carbocation stability. When the carbocation stability is the same, you look at the energy of the reactants, the energy of the alkenes. And we said in a brief hiatus, if we're looking at that alkene is what substitution pattern? That is a tri-substituted alkene. This other one, what substitution pattern is that one? That's a di-substituted alkene. And do you remember which alkene is more stable, which alkene is less stable? The tri-substituted alkene is lower energy because it's more stable than the di-substituted alkene. So, if your carbocations are equal, then you react the less stable alkene. What? You react the alkene that's at the higher energy shelf because you're making an equivalent intermediate regardless. You react that higher energy shelf alkene because the energy input required from that alkene is less. This is a confusing concept, but maybe you get it. This is the product of my reaction. I should specify one equivalent. Man, that's bad habits. I should specify one equivalent of reagent, and this is my one and only product. Yep, that's isolated dienes. What if I have conjugated dienes? Conjugated dienes yield more than one product, even if you only specify one equivalent of reagent. Conjugated dienes yield more than one product. How is that so? We'll talk about it. Hold on. In certain instances, you can control which of your products, because you're always going to make two, in certain instances, you can control which of your product is favored. Let's see. This is a conjugated diene. This conjugated diene, when you add HBr, you're going to get this product and this product. We'll draw a mechanism. Hold on. This product is called the 1,2 addition product. We'll draw a mechanism. Hold on. This product is called the 1,4 addition product. We'll draw a mechanism. Hold on. Depending on the reaction conditions, you can get one of these products to be favored over the other, but you're going to get both products. At negative 80 degrees Celsius, you get 80% this isomer and 20% that isomer. That's interesting. At 40 degrees Celsius, the statistics are opposite. 20% the 1,2, and 80% the 1,4. Why is this so? Why does it work like that? Well, let's draw a mechanism and talk about the details. I have an alkene that is conjugated. That conjugated alkene, they're equally substituted, so it doesn't matter which one I attack that H with. Either one is going to lead to a secondary carbocation. So then that secondary carbocation can be attacked by bromide. Bromide attacks the carbocation, and here we are. That is called the 1,2 product, because if this is carbon 1, that is carbon 2, where did the hydrogen get added? The hydrogen got added to carbon 1, and the bromine got added to carbon 2. This is a 1,2 product, because the two things that got added to the alkene got added 1 and 2. Okay. How do I get the 1,4 addition? Why is that a thing? Well, this carbocation in the middle is a secondary carbocation, but it's also an allylic carbocation. Oh, what does it mean to be allylic? Next door to a pi bond. Not directly connected, but next door to a pi bond. Allylic carbocations have resonance. So the resonance of that carbocation, the resonance of that carbocation leads to the positive charge being concentrated over there. The hydrogen still got added over here, but the positive charge is concentrated over there. The hydrogen's on carbon 1, the positive's on carbon 4. So when bromide attacks here, you get the 1,4 addition product. We're going to point it up because I can't point it the other way. I don't have space. So it's been a hot minute since we talked about resonance stuff. You probably don't think so, but it has a little bit. These carbocations in that green box, what animal might you use to describe those things? Maybe a dragon and a unicorn. What? Yeah. The blue structure does not exist. The purple structure does not exist. The hybrid structure of the two is the rhinoceros that does exist. The hybrid structure says there's a partial positive on that carbon and a partial positive on that carbon simultaneously. This is where students really don't love and don't quite understand resonance. This does not exist. This does not exist. Only this exists. So even when I specify that I'm going to add one equivalent of this, I still get both isomers being created because both isomers came from a rhinoceros carbocation where the positive is in two places at once. Yeah? Did you follow all that? The positive is in both places. The positive is on the 2 carbon and the 4 carbon simultaneously. Is it a full carbon on the 2 carbon, a full positive on the 2 carbon and the 4 carbon simultaneously? No, it's a partial positive on both of them. So there is different stability of this of this dragon and unicorn. There's different stabilities of the green and the, dang it, I don't know my colors. There are different stabilities of the blue and the purple, but they both make this hybrid. So remember, this molecule, this reaction of a conjugated diene will always make 1,2 and 1,4 products even if you only have one equivalent, because the rhinoceros carbocation that exists is positive in both spots simultaneously, so you're going to get 1,2 and 1,4. Okay, dead horse, let's move on. How do I know? Why would I predict that one molecule is favored at high temperatures or low temperatures or whatever? If you look back at our previous slide, it said 1,2 was favored at low temperature. It said 1,4 was favored at high temperature. So to a chemist, we start talking about kinetics and thermodynamics when we start talking about low temperatures and high temperatures and stuff, and we start seeing reaction coordinate diagrams in our head. I know not everybody's like that, but yeah. This low temperature, that's going to be a kinetic product. Kinetic. The high temperature, 40 degrees is not that high, but it's certainly higher than negative 80. That's my thermodynamic product. So apparently, the 1,2 addition product is kinetic in this case, and 1,4 is thermodynamic in this case. Is that always the case? I'm not willing to make that statement. Don't make me make that statement. In this case, 1,2 is kinetic and 1,4 is thermo. We will talk about that kind of stuff a lot later. But let's analyze. The kinetic product comes from, the words I always say are the more stable intermediate. That's a little bit bleh, but the kinetic product comes from the more stable intermediate. This carbocation and this carbocation don't exist, so that's a little bit bleh, a little bit meh, but this is a secondary carbocation. That's allylic. This is a primary carbocation. That's allylic. So this blue is more stable than this purple, so that's why this becomes the kinetic product. That product forms faster at lower temperatures because it has the positive charge on the more substituted carbon. That's deep. This one, the 1,4 product, the thermodynamic product, is not about stability of the intermediates. It's about stability of the product. So why would I say this product is more stable than that product? Well, it's about the stability of the alkene. I have highlighted for you the 2 alkenes. I would say the blue alkene is mono-substituted. That says mono-substituted. I would say the purple alkene is di-substituted. More substituted, more stable. More stable product is the thermodynamic product. Whew. Let's see if I can kind of stick with colors while we draw a reaction coordinate diagram. Reaction progress. Energy. We're starting with a reactant. That's this conjugated diene. We are leading to an alkene, a carbocation that is allylic. This carbocation exists as these 2 resonance structures, but they are not on different energy levels because it's the same carbocation. Okay. Then I have a hump that leads to a product. I want it to be lower than my product. Let's try again. There we go. Lower than my reactant. I have a hump that leads to a product, and I have tried to make this one blue to represent that's the blue product, the 1,2, which in this case is the kinetic product. Kinetic. The purple product should be on a lower shelf because I'm telling you it's a di-substituted alkene. It's a more substituted alkene. But it's going to have to go over a taller hill in order to get to that alkene that's at a lower energy. So it's thermodynamic because that hill is taller. The height of the hill tells me how fast the reaction is. Lower hill, kinetic product. Higher hill, thermodynamic product. It doesn't really go like that. Lower hill, kinetic product. Lower shelf, thermodynamic product. Yeah? It can get kind of confusing, I know, but there we go. Here's a textbook figure that says the same thing, starting from the carbocation, not the reactant the way we did. It's got our 2 traces, lower hill to the kinetic, higher hill to the thermodynamic. It's just a little more pretty clear picture than maybe what I drew. All right. Here's one for you to try. But I guess the first thing you should do, maybe I should point you in the right direction. Does it matter which alkene I choose to react with HBr sort of first? Yes, it does. If you're like so many students, a lot of students would take this alkene because it's closest to the HBr, I don't know. You would take this alkene and react with HBr, and I say, no, don't do that. This alkene, if it reacts with HBr, would create a secondary carbocation. Yeah, it's allylic, but it's a secondary carbocation. If you react that alkene, you can make a tertiary carbocation, and tertiary is better than secondary, so start there and good luck. Okay, so this video is all about dienes and polyenes, and so far we've covered isolated dienes and conjugated dienes, how they react with simple things like acid additions. But conjugated dienes can also do this kind of reaction. So isolated dienes with acids and stuff, done. Conjugated dienes, you have to consider kinetic, thermodynamic, 1, 2, 1, 4, all that stuff when you're doing conjugated dienes with acid additions. But you can also have a conjugated diene react with something that this reaction fancily calls a dienophile, a lover of dienes. You can have a conjugated diene, a dienophile, and those react together to make this cyclohexene. Oh, what? Yeah, this is called the Diels-Alder reaction. The Diels-Alder reaction is a pericyclic reaction, means I'm going to make a cycle. A pericyclic reaction happens like that. 3 arrows all at once. It's a concerted mechanism. 3 arrows all at once. It doesn't matter if I go clockwise or counterclockwise here. It's the same either way. What do I mean by that? I'll draw a tiny little example up here. If I drew these red arrows, it's the 3 arrows going the opposite directions of what I drew with the green arrows. Either one is totally acceptable. It doesn't matter. So I drew the 3 green arrows all at once, diene reacting with dienophile, and I get a cyclohexene. I create this new sigma bond. I create that new sigma bond. And this pi bond flip-flopped there. It's a new thing also. So the pi bond was created between those 2 carbons. Sigma bond was created between these 2 carbons. And a sigma bond is created between those 2 carbons. Yeah? That's Diels-Alder. Diels-Alder is called a 4+2 cycloaddition. 4+2 cycloaddition, what does that mean? How many pi electrons in the diene? 4. How many pi electrons in the dienophile? 2. The pi electrons in the diene and dienophile react together to form this cyclohexene. Does Diels-Alder only happen with 1,3-butadiene and ethene? No. You can put all kinds of fancy stuff off of here, but the diene, the 4 pi electrons from the diene and the 2 pi electrons from the dienophile are what react together to make your cyclohexene. Okay, the reaction can be initiated thermally but not photochemically. That means all I need is a little heat. Delta to us means heat. All I need is a little heat in this reaction to make it go. I don't need any extra reagents like acid or water or anything like that. I'm probably going to dissolve these in a solvent, but I don't need anything extra. All I need is diene, dienophile, and a little bit of heat. This thing works. Overlap is between the HOMO of the diene and the LUMO of the dienophile. That's molecular orbital stuff that we haven't gone into great depth about, and we won't go into great depth about, so do with that what you wish. So this says, dienes locked into S-cis react faster. What is S-cis? If you notice that last diene that I drew, 1,3-butadiene, it was oriented like this. That's called an S-cis conformation. The S stands for sigma, that little lowercase sigma Greek letter. That's because this is a sigma bond, and rotation can absolutely happen around sigma bonds. So that could be in this kind of left conformation, or it could be in this right conformation, which is called S-trans. The S stands for sigma. So rotation around that bond could be like this, could be like that. I don't know. Because rotation can happen, this molecule is not said to be locked into S-cis, but sometimes it rotates to an S-cis conformation. However, it's actually more stable as the S-trans conformation because there's more real estate, there's more room for everything to spread out. The biggest stuff is as far apart as it can possibly get when it's an S-trans conformation. So if I go through my examples over here, this guy looks like he's in an S-trans conformation. This guy looks like he's in an S-cis conformation. This guy looks like he's in an S-trans conformation as well. So what does that do for me? What does that mean? We said this one's S-trans. We said this one's S-cis. We said this one's S-trans. So I didn't say, but should have, the diene has to be in an S-cis conformation to react whatsoever. Because this guy, this diene, is tied into a ring and rings cannot rotate, this alkene, this diene, is in an S-trans conformation and has no chance at ever reacting in a Diels-Alder kind of reaction. This one has no chance. The S-cis conformation, the middle ring, my laser stuff's not showing up, the middle ring says, or the middle ring is locked into S-cis because of the same reason that one's locked into S-trans, this one is locked into S-cis because it's in a ring and rings can't rotate. This very first one, it's actually 1,3-butadiene. It's the same thing that we just saw. Rotation can happen to put this into an S-cis conformation, but it spends more time in the S-trans. So if I were ranking these characters, I would rank the middle one as number 1, it's the fastest. The left one as number 2, it's the slowest. And I would not rank number 3 I would not rank the right one as number 3 because it doesn't react in diene in Diels-Alder whatsoever. If you did put number 3, that's acceptable-ish because the fact is it is slow, but it's so slow that it never happens. Yeah? All right. These bottom 2 points down here we're going to talk about and we're going to draw examples of. Start with this second one. Electron withdrawal increases reactivity of dienophiles. Here are some dienophiles. That bullet said electron withdrawing groups increase reactivity of dienophiles. So it must mean that this, and this, is kind of all the same. It must mean all those blue circled things are electron withdrawing groups. How do these things withdraw? They all withdraw through induction, yes, but also resonance. Let's draw some resonance to prove how these things withdraw electrons. What I'm trying to draw resonance to show, to prove, is that these dienophiles, yes, they're normal alkenes, but we're calling them dienophiles when we're talking about Diels-Alder. These dienophiles are not as electron-rich as something that has all hydrogens and no other group attached. So I'm trying to draw resonance to prove that the yellow highlighted things are less electron-rich than the blue thing over there. So I'm going to start out by not drawing CN like that. I'm going to draw my CN triple bonded like that. I'm going to start out by pulling electrons toward the nitrogen. So if we go all the way back to week 1, a pi bond exists between atoms of different electronegativity. Yeah. Always give the electrons to the more electronegative atom. Electrons go toward the more electronegative atom. So electrons go toward the nitrogen, taking away from that carbon, like that. I have a positive charge that's next door to a pi bond. This is an allylic carbocation now. Swing that door over there. My hinge is in the corner, and I get this. What's the point of me drawing this resonance down here? To prove that my yellow highlighted dienophile has less electron density than the blue alkene over there. We can maybe highlight that alkene in blue as well, but a different shade. We're trying to prove that my yellow highlighted dienophiles have less electron density than my blue highlighted dienophile. So because I drew these resonances and one of my dienophile carbons now has a positive charge on it, that's telling me that this cyanide, Cn-, this Cn- is actually withdrawing electrons from that yellow dienophile. Cyanide is an electron withdrawing group. Okay, This is also an electron withdrawing group. How am I going to start the resonance? A pi bond exists between atoms of different electronegativity. The pi electron should always go toward the more electronegative atom. Okie dokie. Toward the more electronegative atom. We're going to squeeze that down here. O minus, C plus, pi bond. All right. I now have an allylic carbocation. Swing it all around. Do-si-do. O minus, new pi bond, positive charge down yonder. These guys look awfully similar to me. I'm showing a positive charge on the dienophile carbons in both of those. That's proof to me that this blue circle, that blue circle, contains an electron withdrawing group. I ran out of space, but I could draw these guys, but you could also draw these guys, the resonance for the right-hand molecule, right? Right? Yeah, I think you could. The difference in these molecules is that the left two, the left one and the middle one, those are both not symmetric dienophiles. The third one is a symmetric dienophile, and that's going to have an impact down the line when we do more Diels-Alder. All right. Characteristics of good dienophiles. Good dienophiles have electron withdrawing groups. All righty. Good dienes have electron donating groups. So we're going to try to show how this purple circled group must be an electron donating group. So it's considered a donating group when this diene has more electron density than a standard diene. If we try to do the same colors as the last one, a typical diene, the simplest diene that can do Diels-Alder, that's 1,3-butadiene, like that. There are hydrogens connected all around that thing. We're trying to prove that the yellow highlighted diene has more electron density than the blue highlighted diene. So we're trying to show that the purple circled thing is an electron donating group. So I'm going to start with a lone pair is conjugated with a pi system. That's situation number 5, throwing it way back. A lone pair is conjugated with a pi system. The lone pair donates toward the pi system, like that. That would explode this corner carbon octet, so we got to move that pi bond out the way. All right. I draw the resonance of that. Pi bond down there was not bothered. I get a positive charge on that oxygen and a lone pair out there on that carbon, giving that carbon a negative charge. What were we trying to prove? We were trying to prove that the yellow highlighted diene has more electron density than the blue highlighted diene. I got a negative charge on my diene carbon over there. Proof. This diene has more electron density than that one due to this purple circle that I had to erase, due to this purple circled group being an electron donating group. That was involved, but hopefully it made some sense to you. Diels-Alder reacts a diene and a dienophile. The reaction is concerted. All reactions that are concerted lead to syn addition. Syn addition. Be careful. Syn addition does not necessarily mean a cis product. Wait, what? Syn addition does not necessarily mean a cis product. This alkene in the middle, this alkene that is my dienophile, this alkene is a cis alkene. My two groups are pointed the same direction. There are also two hydrogens here pointed the same direction. That's a cis alkene. In the end over here, I got a cis product. Because the reaction is concerted, whatever configuration of the dienophile you have here, that configuration of the dienophile must stay the same in the product. It was cis here, it has to be cis there. If it's trans here, it has to be trans there. So, Sometimes when I say the reaction is concerted, students think, oh, that means it always makes a cis product. Concerted means happens all at once. So if you could see my hands, it's real hard to do this without pointing things. This planar structure has to hover over this planar structure. My laser is not showing up. Oh, the struggles today. This planar structure, dienophile, hovers over or under this planar structure, diene. The two planar things have to hover next to each other in order to react. The reaction happens all at once. It's a concerted thing. Pi bond goes here, pi bond goes there, pi bond goes there. 3 arrows all at once. Everything's happening all together. Because it's two planar things reacting, whatever stereochemistry you start with, you lock in that stereochemistry. Yeah. All right. Page 321 has a small paragraph. It's probably not page 321. My PowerPoint has crashed 3 times while trying to record this video, and so I have edited that, and it has changed. Give me 1 second to give you the real page number. Yep, I'm a professional. It's page 321 in the 7th edition of the textbook. It's page 361 in the 8th edition of the textbook. I apologize. All right. If the diene is cyclic, the product is bicyclic. Huh, what? If the diene is cyclic, the product is bicyclic. Here's how my curved arrows go. I'm creating this 6-membered ring. 1, 2, 3, 4, 5, 6. Diels-Alder always makes a cyclohexene. But this carbon was in the middle of carbon 1 and 4. When carbon 1 and 6 made a new bond, and carbon 4 and 5 made a new bond, it did not disturb that carbon in the middle whatsoever, so that carbon in the middle still needs to be shown. The way that it's drawn over here on the right, the way the product is drawn, is not typically the way we draw bicyclic molecules. Whew, are you ready for this? The bicyclic molecule is typically drawn in a structure like this. Oops, that's supposed to be double O. It's typically drawn in a structure like this, where we have a carbon pointed up and out of the plane of these others. That carbon up there, that's my blue highlighted carbon. That's the carbon that was connecting carbon 1 and 4 in my numbered carbons up above. It's hard to draw conformations like this. I'm not super great at it, especially when I'm trying to squish it down here. So let's look at an image where the computer has drawn it. The way it works is this flat molecule has to approach this flat molecule. Oh, my laser. So these two molecules need to come in close contact in order to react. I said this flat molecule and that flat molecule. Well, the right molecule, the dienophile, is a flat molecule, but the diene is not flat. That carbon, that CH2 carbon, has to, it's in a different plane. That CH2 carbon needs to be pointed a different direction so that these two carbons can be near each other in order to hook up and make my 6-membered ring. Okay, so that's how this little point up top is created when I make this bicyclic structure. It's 2 fused rings in a bicyclic molecule. So I'm not explaining this super well because my PowerPoint is continuing to freeze and cause issues. So I'm going to shut it down and wrap it up. These 2 ways are how you can draw the 2 separate products that could be created. These 2 products on the right are diastereomers. They have some stereocenters the same and some stereocenters, dang it, some stereocenters the same and some stereocenters different. These 2 are different. These 2, those 2 are the same. So these are diastereomers. Both of these compounds are actually meso compounds. That's why we don't have so many isomers created here. But these two products have further classifications to discuss their structures. I don't know really how I want to say that. This one is called the exo product. This one is called the endo product. Your book has a little bit more information about that. Endo and exo is not something we will discuss at length. It's not something I expect you to know at length. But endo and exo are how you would describe these two diastereomers. Exo has your substituents hanging, like pointing outward on your bicyclic thing, while endo has your substituents pointing sort of inward on your cycloalkene thing, making this sort of cup-like shape in this molecule and a flat-like molecule up there in exo. All right, I'm ready to wrap this up because PowerPoint's making me crazy. I hope it can hold out for a little bit longer. If it can't, we're going to shortcut it right here. All right, alkene attacks, alkene attacks, alkene attacks. Folds it down. We end up with a cyclohexene. 1, 2, 3, 4, 5, 6. Those are where my new bonds are made. I'll put carbon 7, 8, and 9 on there as well. 1, 2, 3, 4, 5, 6. New alkene between 3 and 2. Carbon 7 and 8 are still connecting carbon 1 and 4, and carbon 6 still has carbon 9 on it. That's really wonky the way I drew it. That's because it should be drawn in a bicyclic conformation, like this. Where I have 2 carbons, actually I want to point that this way, 2 carbons across the bridge up top. 2 carbons up there, that's carbons 7 and 8 up there. And it's a cyclohexane, like the others that we've seen, carbon 7 and 8 across the top of that bridge. That product that I've drawn there is the exo product. The endo product would look like this, where that carbon of your aldehyde is pointed straight down instead of sort of out. It would make both endo and exo products. Those products are diastereomers. Whew. Next, flip it, flip it, flip it. Cyclohexene. 1, 2, 3, 4, 5, 6. Carbon 1 and 2 are going to have a pi bond. Based on how I decided to do my numbering this time, I chose differently. Carbon 1 and 2 are going to have methyl groups on them. Carbon 4 and 5 have CO2-mes, esters. What else is missing? Carbon 4 and 5 were an alkyne. Alkynes, you're breaking one of the pi bonds, but one of the pi bonds stays. What makes that awesome? There are no asymmetric carbons in this. You don't have to worry about enantiomers, diastereomers stuff. You don't have to worry about bicyclic things because it's not a bicyclic compound. Whew, yeah, bicyclics are messy. So for Diels-Alder reactions, what are your expectations? You need to be able to predict the products of Diels-Alder, and you need to be able to recognize that a molecule could be made through a Diels-Alder reaction and tell me the products or the reactants that were used to make that thing. So synthesis with Diels-Alder, you got to be decent with that as well. There's one final topic of Diels-Alder stuff on page 358 of the 8th edition of the book. That page 358 is important with regards to unsymmetrically substituted dienes and dienophiles. If you look back through the examples we've walked through, all of the examples where we drew a product that was the result of either both the diene and dienophile being symmetrically substituted, or one was symmetric and one wasn't. If both your diene and dienophile are not symmetric, as in both of them are unequally substituted, You get some interesting results sometimes. You should check out page 358 if you don't check out any other textbook pages. All right, let's bring it in for a close. Diels-Alder was a 4+2 cycloaddition because there were 4 pi electrons reacting with 2 pi electrons. The 4+2 was thermally allowed. The 2+2 cycloaddition is thermally forbidden, but photochemically allowed. If you flip back to our first page where we started talking about Diels-Alder, we said the opposite. 4+2, thermally allowed, photochemically forbidden. 2+2 is the opposite. A 2+2 cycloaddition, well, it happens like that, and you end up with a square. Isn't that silly? And you think, is that a useful reaction? Well, it's not particularly useful for what we talk about in organic, but it is actually something that happens all the time in actual life. So these are thymine bases, DNA bases. The alkenes in DNA, the alkenes in thymine, when exposed to ultraviolet light, like from the sun, that DNA can dimerize, is what it's called. What you end up getting is a little square. This attacks that, this attacks that, you get the little square like we just showed on the previous slide. That's what's different about thermochemically allowed and photochemically allowed. UV radiation is what initiates this reaction. Do you think it's great if all of your DNA dimerizes? Not so much. It's processes like that can lead to cancer stuff. Kind of cool. I'm frustrated with all my stuff, so I'm calling this